Hi friends, thanks for checking my channel. Today we are going to discuss all the things that happen behind the scenes when you run a Kafka cluster without Zookeeper, that is Kraft mode. Let's see what we have for our agenda today. First, we will start with revisiting the architecture of a Kafka cluster today, that is a Kafka cluster that runs with Zookeeper. Then, we will discuss in detail about all the problems that we face in a Kafka cluster today because of the presence of Zookeeper, the most important problems centered around complexity and scalability of a Kafka cluster. And then we will see what is the logic that we could apply for removing the Zookeeper completely from the Kafka ecosystem. And then we will discuss in detail about the architecture of a Kafka cluster without Zookeeper, that is, running a Kafka cluster in Kraft mode. Followed by this, we will see what is actually a Kraft protocol on a very high level. And then we will discuss about the advantages of running a Kafka cluster in Kraft mode over a Kafka cluster that runs with Zookeeper. And finally, we will wind up the session by giving some information on the release of Kraft protocol as well as some information on migrating a Kafka cluster that runs with Zookeeper to a Kafka cluster in Kraft mode. So let us start with revisiting the architecture of a Kafka cluster that runs with Zookeeper. Now we are seeing an example for a 3-node Kafka cluster, that is a Kafka cluster with 3 brokers. Brokers are the systems or the nodes where the actual application data will be stored. If you are sending any data to your Kafka cluster, this means these data will be stored inside the brokers. Inside the brokers, all this application data will be aggregated into a logical unit called as Kafka topic. You can consider a Kafka topic equivalent to a table inside a database. For example, if you are sending any customer related data to a Kafka cluster, all this customer data will be aggregated into a single topic. We can call this topic as customer topic. And then inside this Kafka topic, we have partitions. Partitions are the actual units of data storage. That is, they represent the space inside the disk where the data will be stored. So now we are seeing an example for a single Kafka topic that is having a single partition labeled as P0. In reality, a Kafka topic can have any number of partitions. And then each partition can have multiple copies. We call such copies as partition replicas or simply replicas. In this example, we are seeing that this partition P0 is having 3 replicas, one on each broker. The maximum number of replicas that a partition could have is equal to the total number of brokers inside the Kafka cluster. In this example, we are having 3 replicas because in total we have 3 brokers. But you can also have 2 replicas or simply 1 replica. Replicas ensure the high availability of the Kafka data. Now we are seeing this replica highlighted in green color. This is the leader replica, whereas the remaining 2 are the follower replicas. Leader replica is the one where all the writes will happen. So if you are sending any data to your Kafka broker, that is your Kafka topic, that is your Kafka partition, all this data will be written only to the leader replica, and then the follower replicas will be updated. The applications that sends the data to the Kafka cluster are called the producer applications, whereas the applications that read the data from the Kafka topic are called as consumer applications. So as you could see, all the data that is written by the producer are written only to the leader replica, and then the follower replicas will be updated. Similarly, all the data that are read by the consumers are also read only from the leader replicas. Now, what happens if this broker that is containing the leader replica fails? Then, among the remaining 2 follower replicas, one of them has to be elected as the new leader. This is where the controller comes into action. Controller is nothing but one of the brokers inside the Kafka cluster. That is, just like other brokers, controller also stores Kafka topics. But in addition to that, it is mainly responsible for performing any metadata management activities inside the Kafka cluster. For example, administration of partitions. It elects leader replica for any partition. It also keeps track of the state of all the partitions inside the Kafka cluster. That is, which partitions are online and up to date, which partitions are offline and out of date, which partitions are deleted and removed from the Kafka cluster. It also stores the cluster information, that is, configuration of the Kafka topics, configuration of the entire Kafka cluster, security credentials like username and password when you create while communicating to the Kafka cluster, IDs of the broker, location of partitions like which partitions are located on which brokers, and then most importantly information about ISR, that is in-sync replica. So what is actually in-sync replica? So imagine the ID of this broker is 0, ID of this broker is 1, and then this broker is 2. Then the ISR, that is the in-sync replica for this partition P0 will be 0, 1 and 2 because all these 3 replicas are online and up to date. Suppose if this broker fails, then the ISR for this partition P0 will be 0 and 2 because the broker number 1 has failed and so we lost this replica. So this is all about in-sync replicas. Now, what happens if this broker that is acting as the controller also fails? Then, among the remaining brokers, one of them has to be elected as the new controller. This is where the Zookeeper comes into action. Zookeeper is an Apache application that runs entirely outside of the Kafka cluster. In reality, you can have either a single Zookeeper or a cluster of Zookeepers. We call this as Zookeeper ensemble. Zookeeper is mainly responsible for electing the controller to operate the Kafka cluster. In addition to that, Zookeeper also acts as the single source of truth for the Kafka cluster. That is, all the metadata information kept track of by the controller will be permanently stored inside the Zookeeper. So the Zookeeper stores metadata mostly from the controller. That is, for example, topic configs, location of partitions, information about ISR, and so on. Similarly, brokers also stores some kind of metadata into the Zookeeper from time to time. Also, other Kafka clients like producers, consumers, Kafka ACLs, Kafka configs also store some kind of information into the Zookeeper from time to time. I have explained about all these Kafka clients in my previous videos. So whenever you are starting a Kafka cluster, the Zookeeper will first elect a controller. Similarly, whenever an existing controller fails, the Zookeeper will elect a new controller. So whenever a controller is elected, the controller will first load the entire metadata from the Zookeeper. Only then the Kafka cluster can operate. So the communication between the Zookeeper and the controller is very important for operating the entire Kafka cluster. So this is how the Kafka cluster has been operating until today with the help of Zookeeper. Then why the Zookeeper need to be removed? If you look into the whole diagram, you could observe two different things. First, both the Zookeeper and the Kafka are two different systems. They are not the same system. Then we are managing the metadata of the Kafka cluster entirely outside of the Kafka cluster, that is inside Zookeeper. We call this as external metadata management. Because of these two different things, today we are facing some problems that limits the usability as well as the scalability of the Kafka cluster. We will see them one by one in detail. So first, Zookeeper and Kafka are two different systems. Zookeeper is an Apache server application that is responsible for coordinating the operations of a distributed system. For example, it performs metadata management in distributed systems. It also provides a file system API on top of a log data structure. So log is nothing but the partitions that we discussed before, that is the area on the disk where the actual application data will be stored. Whereas Kafka is an Apache application that provides a distributed event streaming platform. Kafka provides a PubSub API based on an event-driven architecture on the top of a log data structure. Because Zookeeper and Kafka are two different systems, it now adds more and more complexity for the Kafka administrators. This is because Kafka admins now have two different systems to manage. This means they need to handle two different implementations for configuration, security, monitoring, and networking. Similarly, if they want to tune the performance of a Kafka cluster, this means they need to apply two different performance optimization mechanisms, one for Zookeeper and the other one for Kafka. The next problem we see today because of the presence of Zookeeper is Kafka is often viewed as a very heavyweight infrastructure. This is because Kafka is not a single process deployment. If you want to deploy a Kafka cluster, this means you also need to deploy a Zookeeper. Because of this, most of the startup companies normally consider only small scale messaging systems like RabbitMQ to start with. They consider Kafka only when the scale demands, which is not true. Kafka can also be used for small scale loads and can still bring a lot of benefits. So to summarize, because of the Zookeeper and Kafka being two different systems, it adds more and more complexity for the Kafka administrators, and Kafka is viewed as a very heavyweight infrastructure. The next problem we face today because of the presence of Zookeeper and managing the metadata externally inside Zookeeper is the limitations associated with the scalability of the Kafka cluster. First, what is scalability in Kafka? Scalability means ability to add more and more number of partitions to support more data inside Kafka. Since we are managing the metadata externally inside Zookeeper, this directly limits the scalability of the Kafka cluster. This is because there are certain operations inside Kafka cluster that requires moving the metadata between Zookeeper and controller. The time for such operations is equal to the order of total number of partitions inside the cluster. Some of the examples for such operations: controlled shutdown, uncontrolled shutdown and recovery, controller failover and recovery. We will see all these operations one by one in detail later. So whenever we are trying to increase the total number of partitions, this means the metadata about such partitions will also increase, and this means the amount of the data, that is the amount of the metadata that we need to move between the Zookeeper and controller, will also increase, and this means the time for any such operations which require moving the data between the Zookeeper and controller will also increase. So whenever the time for such operations increases, this directly impacts the performance of the Kafka cluster. So because of this, we cannot scale the Kafka cluster beyond a certain limit. If we try to add more and more partitions beyond a certain limit, then obviously the metadata will grow, and then the time for all such operations will increase, and then this will impact the performance of the cluster. The next problem we have because of managing the metadata externally inside Zookeeper is divergent views. The metadata information that we persist inside Zookeeper and controller may not be in sync all the time. Just like controllers, brokers also cache the metadata views from time to time. This metadata view from the brokers may not also be in sync with the controller. We will discuss about divergent views in detail later. Now we will see all those performance impacting operations one by one in detail. First one is controlled shutdown. Controlled shutdown is an activity that is performed during rolling restart, that is one broker at a time. We perform this controlled shutdown whenever we want to upgrade the software inside the brokers one at a time, or whenever we want to upgrade the version of Kafka inside all the brokers one at a time. Whenever we perform controlled shutdown, the availability of the cluster will not be impacted. Now let us see how this controlled shutdown takes place. We are now having a set of brokers. Let us assume that the ID of this broker is 0, this broker is 1, this broker is 2, and this broker, which is also acting as the controller, is 3. We now have a Kafka topic with two partitions, PA and PB. For both of these partitions, we have three replicas, one on the broker 0, one on the broker 1, and the other one on the broker 2. For both these partitions, the replica on the broker 0 is the leader replica. That's why we see the leader for the partition PA is 0. Similarly, the leader for the partition PB is 0. As you could see, the controller also keeps track of the leader information, and in addition to that, it also stores the ISR information, that is the in-sync replica. So here the in-sync replica for the partition PA will be 0, 1 and 2. That is, for the partition PA, the copy or the replica on the broker 0, broker 1 and broker 2 are in sync and up to date. Similarly, for the partition PB, the replica on the broker 0, broker 1 and broker 2 are in sync and up to date. The controller will also store this information inside the Zookeeper. In reality, all these brokers will also have a view of the ISR information locally on their cache, and this ISR information on the brokers will be updated by the controller. However, I have not highlighted the ISR on the brokers here in this diagram. Now, if you want to do a controlled shutdown on this broker 0, first a SIG-term signal will be sent to this broker. Then this broker will notify the controller that it is going to shut down. Then the controller will elect a new leader for both these partitions PA and PB one by one, and then it will also update the ISR information one by one. So now you could see that the controller has selected the new leader for this partition PA and PB, that is the replica on the broker 1 will be the new leader for this partition PA and PB. Similarly, the controller will also update the ISR information. So now you could see the ISR is 1 and 2, because the broker 0 is going to shut down very soon, and hence it has removed the replica 0 from the ISR list. Once this is done, the controller will then persist this information for both these partitions one by one inside the Zookeeper. So once this persistence is over, then the controller will propagate the information about the new leaders and the ISR information to all the brokers one by one. And finally, the controller will ask the broker to shut down, and then this broker 0 will shut down. In case of controlled shutdown, any producer and consumer traffic happening on the impacted partitions PA and PB will still be happening only on the old leaders. Only after the new leaders are elected and the new updated information is propagated to the remaining brokers, the producer and consumer traffic will be moved to the new leaders. Thus, in a controlled shutdown, the system availability will not be impacted. The overall operation time required to perform a controlled shutdown is equal to the total time required to persist this updated information inside the Zookeeper and the total time required to propagate the updated information inside the remaining brokers. Here in this example, we have only two partitions. However, in reality, we may have lots and lots of leader partitions on the impacted broker, and hence we may have lots and lots of metadata to be moved to the Zookeeper from the controller. Also, please note that the controller will persist the information inside Zookeeper only for one partition at a time. Hence, as the number of partitions increases, the number of metadata increases, and this means the number of I/O requests between the controller and the Zookeeper will also increase. One thing that we need to note about the control shutdown is that it does not include the time for the leader election. So until the new leaders are elected, any producer and consumer traffic can still happen on the old leaders, that is on the old broker, since it is not yet shut down. So thus, the overall operation time required for the control shutdown is equal to the order of the total number of partitions. So as you increase the number of partitions, the number of metadata also increases, and hence the amount of metadata that we need to move from the controller to the Zookeeper will also increase. So hence we cannot scale the Kafka cluster beyond a certain limit, and if we do that, the time for the control shutdown will also increase. Now we will see what is actually an uncontrolled shutdown. Uncontrolled shutdown is very similar to a controlled shutdown, with the only difference is that the broker will shut down abruptly without any prior notification to the controller, for example in case of a system crash. So now let us imagine that this broker 0 has crashed abruptly. Now the controller has to elect a new leader for all the leader replicas that are hosted on the impacted broker. So in this case, controller will elect a new leader for the partition PA and PB, and then it will also update the ISR list. So once it is done, then it will persist this new information inside the Zookeeper, similar to what we saw in the control shutdown. And after the persistence inside the Zookeeper is over, then the controller will propagate the new leaders and the new ISR information to the remaining brokers. The main difference between a controlled and uncontrolled shutdown is, in case of an uncontrolled shutdown, whenever a broker crashes abruptly, then the controller will be put under immense pressure to elect new leaders for all the impacted leader replicas that has been hosted on the crashed broker. This is because until the new leaders are elected, any producer or consumer traffic coming for the partitions PA and PB will be unavailable. This is because for both these partitions, the controller has not finished electing a new leader yet. Thus, the producer and consumer request for such partitions will time out. Hence, the overall operation time required to perform a recovery from the uncontrolled shutdown includes the time for the leader election as well, in addition to the time required to persist the updated metadata information inside the Zookeeper and the time required to propagate all these updated new leaders and ISR information to the remaining brokers. The overall operation time required to perform the recovery from an uncontrolled shutdown is equal to the order of the total number of partitions. This is because in this example we have seen only 2 partitions, but in reality we may have lots and lots of partitions. Therefore, as the number of partitions increases, then the time required for performing each of these operations will also increase. However, similar to a controlled shutdown, also in the case of an uncontrolled shutdown, the most performance impacting operation is the operation where we persist the information inside the Zookeeper. This is because this is the operation where the controller has to move the data externally to the Zookeeper. Therefore, as the number of partitions increases, then the amount of the metadata need to be moved to the Zookeeper is also likely to increase, and hence the time required to move such metadata is also likely to increase. Hence, we cannot scale the Kafka cluster beyond a certain limit, and if we do that, then the overall time required to perform a recovery from the uncontrolled shutdown will also increase. Now we will see what is actually a controller failover. In this example, we now have for these partitions PA and PB 4 replicas on all the 4 brokers including the controller, and the replica on the controller is the leader replica for both these partitions. That's why you see the leader for the partitions PA and PB as broker 3, that is the controller. Similarly, the in-sync replica list includes all the 4 broker IDs. Now, what happens if the controller fails? First, the Zookeeper has to elect a new controller. Then, the new controller has to load the complete metadata information stored inside the Zookeeper. Then, for every leader partition that has been hosted on the failed controller, the new controller has to elect a new leader and then update its ISR list. So now you see the new controller has elected a new leader for both these partitions, that is the broker 0, that is the controller itself, and then it also updates the ISR list. Once it finished updating these 2 information, then it will persist the new updated information inside the Zookeeper. And finally, the new controller will propagate all the updated ISR as well as the leader information to the remaining brokers. Thus, the time for the overall recovery from the controller failover includes the time for the new controller election, the time for loading the entire metadata from the Zookeeper, and then the time for electing the new leader for all the impacted partitions, and the time required to propagate this new information inside the Zookeeper, and finally the time required to propagate the updated information to the remaining brokers. The most important thing that you need to be aware of the controller failover is, until the metadata loading process is done. That is, until the controller finishes loading the entire metadata from the Zookeeper, the entire Kafka cluster will be unavailable. This is because only after the new controller has the complete metadata from the Zookeeper, it can start operating the Kafka cluster. The time required to load this entire metadata from the Zookeeper is equivalent to the order of the total amount of partitions inside the Kafka cluster. That is, as the number of partitions increases, then the amount of metadata stored inside the Zookeeper also increases, and hence the time required for loading this entire metadata from the Zookeeper by the new controller also increases. Once the metadata loading process is done, then any producer or consumer traffic coming for the impacted partitions PA and PB will also be unavailable. This is because the new controller has to finish electing the new leaders for those partitions as well. Until then, any producer or consumer traffic for such partitions will time out. This is similar to what we saw in the case of an uncontrolled shutdown. The overall time required to perform a recovery from a controller failover is equivalent to the order of the total amount of partitions. That is, as the number of partitions increases, then the time required to perform each of these operations also increases. However, the most performance impacting operations are the ones where the new controller has to load the entire metadata from the Zookeeper, and then the new controller has to persist the updated leader information and the ISR information inside the Zookeeper, similar to what we saw in the case of a controlled and uncontrolled shutdown. Now we will see some facts about all these three operations. With Kafka version 1.1.0, we started using asynchronous API for persisting any metadata from the controller to Zookeeper, as well as for reloading the metadata from the Zookeeper by the controller. Before the introduction of asynchronous API, the controller used to handle only one partition at a time. That is, whenever it wants to persist the metadata to Zookeeper, it will handle only for one partition at a time. Similarly, whenever it wants to reload the metadata from the Zookeeper, it will reload only for one partition at a time. However, after this asynchronous API was introduced, controller can now handle multiple partitions at a time. With this, we saw a significant reduction in time for all these three operations. Now Kafka can support up to 200,000 partitions in the best case. However, based on our discussion so far, we could easily understand that if there is no need to write any metadata to the Zookeeper, then we could have seen even more reduction in time for all these three operations, and consequently, Kafka could have supported more than 200,000 partitions very easily. The next problem we see today, because of managing the metadata externally on the Zookeeper, is divergent views. As we discussed before, the communication to the Zookeeper mostly comes from the controller, as well as from the brokers from time to time, as well as from the Kafka clients like producers and consumers. However, in order to reduce the load on the Zookeeper coming from the Kafka clients, such load is already moved from the Zookeeper to directly brokers. That's why in the recent releases of Kafka, you would have noticed that whenever you want to write a producer or consumer application, you would not use the flag called Zookeeper. Instead, you would use a flag called bootstrap server, that is address of list of brokers. That is, whenever you want to write a producer application, you will specify the address of a list of brokers, and then a random broker will be consulted by default, and this random broker will redirect the producer traffic to the actual broker that contains the leader partition for the topic to which the producer wants to write the data. That's the reason all the brokers also maintain the ISR information, and this ISR information will be updated by the controller by means of RPC calls. Therefore, we can understand that the metadata information will be stored inside the Zookeeper. It will also be stored inside the controller, and the view of this metadata will also be maintained in the local cache of the brokers. With this, we observed that the metadata view between the controller and the Zookeeper may not be in sync all the time. This is because the controller keeps track of all the latest metadata information, and only then it persists the updated metadata information inside the Zookeeper. Therefore, if you write a producer application that wants to communicate to the Kafka cluster using the Zookeeper flag, and if the Zookeeper does not have the latest ISR information, then all the producer requests will time out. Similarly, the metadata view between the controller and the brokers may not be in sync all the time. This is because the controller will first write the updated metadata information to the Zookeeper, and only then it will it will propagate the updated ISR information to the brokers. So if a producer application uses a bootstrap server flag for communicating to the Kafka cluster, and if the brokers does not have the latest ISR information, then all such producer requests will also time out. So thus we saw that using the Zookeeper can lead to more and more divergence of the metadata view between the controller and the Zookeeper, as well as between the controller and the brokers. And more amount of divergence means more amount of client request timeout, whenever the clients try to communicate to the Kafka cluster. Now, let's try to summarize all the problems that we are facing today because of having Zookeeper inside a Kafka ecosystem. First, because of Zookeeper, it adds more and more complexity for the Kafka administrators because the Kafka administrators now have two different systems to implement and manage. Then, Zookeeper makes Kafka to be perceived as a heavyweight infrastructure. This is because Kafka is not a single process deployment. If you want to deploy Kafka, you also need to deploy a Zookeeper. Then, having Zookeeper and managing the metadata externally inside the Zookeeper limits the scalability of the Kafka cluster. That is, you cannot add more number of partitions beyond a certain limit, and if you do that, it will affect the performance of the Kafka cluster. Then, managing the metadata externally inside the Zookeeper also leads to divergence of metadata views among Zookeeper, controller, and brokers. Because of all these reasons that we discussed so far, Kafka community decided to eliminate the Zookeeper completely from the Kafka ecosystem. Now, let's see what is the logic that we could apply for removing the Zookeeper completely from the Kafka ecosystem. So far, Zookeeper has proven to be a great tool for managing the metadata of the Kafka cluster efficiently. Therefore, if we are going to remove the Zookeeper completely from the Kafka ecosystem, then moving forward, how are we going to manage the metadata of the Kafka cluster? In order to understand this, let's try to first understand what exactly we are doing with the Zookeeper today. If you look into the Zookeeper, inside the Zookeeper, the metadata is stored as a sequence of change events. That is, we are not storing the metadata as a snapshot but as a sequence of change events. And if you look into Kafka, whatever application data that we are sending to a Kafka cluster, these data will be stored as a sequence of events inside the Kafka partitions. And these events will be ordered by the offsets, that is, based on the order of their arrival. Another important activity that the Zookeeper performs today is the controller election. Whenever you are starting a Kafka cluster, then the Zookeeper has to elect a controller for the entire Kafka cluster to operate. Thus, Zookeeper supports a protocol for election. If you look into Kafka cluster, if a Kafka partition has multiple replicas, then one of the replicas has to be elected as the leader replica. And this election is done by the controller. That is, Kafka also supports a protocol for leader election. So, the two most important concepts that the Zookeeper supports today, that is, storing the data as a sequence of events and then support for an election protocol. Both these concepts are also available inside Kafka. This actually sparked the initiative for the Kafka community to take advantage of both these concepts supported by the Kafka and move the metadata management inside Kafka itself. And this initiative was started as part of KIP-500, that is Kafka Improvement Proposal 500. So, moving forward, the metadata of the Kafka cluster will be stored inside Kafka itself rather than separately inside Zookeeper. We refer to this way of managing the metadata as Kafka on Kafka. That is, the metadata of Kafka will also be stored inside Kafka, or log of logs. That is, similar to how we are storing the application data inside Kafka partitions, the metadata of the Kafka will also be stored inside a Kafka partition. That is, information or metadata about Kafka partitions will also be stored inside a separate Kafka partition. Now let's start taking a deep dive into the brand new architecture of Kafka. That is the architecture where we are not going to use Zookeeper anymore, but instead we are going to manage the metadata of Kafka inside Kafka itself. So whenever we are running Kafka without Zookeeper, we call this mode as Kraft mode. I will explain what is the reason behind calling this mode as Kraft mode later in this video. So moving forward in this new architecture, we will not be having the Zookeeper anymore. Instead, we will be having only the Kafka nodes. Each node can be configured to act only as a broker, or can be configured to act only as a controller, or each node can be configured to act both as a broker as well as a controller. The nodes that we have configured to act only as a broker are called broker nodes, whereas the nodes that we have configured to act only as controller are called as controller nodes, whereas the nodes that we have configured to act both as a broker as well as controller are called as combined nodes. In this way, we separate the control plane totally from the data plane. That is, for example, all the nodes that are acting as controllers will have their own port, and that port will be used by the brokers for connecting to the controllers and communicating to them. Similarly, all the nodes that are configured to act as brokers will be having their own port, and that port will be used by Kafka clients like producers and consumers for communicating to the brokers. For example, today we are using port like 1992 or 1993 for the producers and consumers to connect to the brokers. Similarly, the controller nodes will be having their own port, and that port will be used by the brokers for communicating to the controller. And then All these nodes that are acting as controllers will all together form a quorum. We call this as quorum of controllers or simply a quorum controller. I will explain what is quorum later in this video. Now, all these controller nodes that are part of this quorum controller will all together manage an internal topic called as metadata topic. It is in this metadata topic that we are going to store the entire metadata of the Kafka cluster. Previously, we have been storing the metadata of the Kafka cluster inside Zookeeper, but now we are going to store the metadata of the Kafka cluster inside Kafka itself by means of this internal metadata topic. We call this metadata topic as underscore underscore cluster underscore metadata. Similar to how we store the data inside a Kafka application topic, the metadata will be stored inside this metadata topic and they will be versioned by means of offsets. That is, we can identify the latest metadata by means of its offset number. For example, in this metadata topic, we have three different metadata information and each of these metadata information are identified by means of their offset number, that is O1, O2 and O3. So O3 is the latest metadata. This metadata topic will always be created only with one partition. That is, whenever you are starting a Kafka cluster without Zookeeper in Kraft mode for the first time, this metadata topic will be created by default and this topic will always be having only one partition. For this reason, we call this either as a metadata topic or simply as metadata partition or metadata log. Now every controller that is part of this quorum controller will be having a replica of this metadata partition. So now we have three nodes acting as controllers and all of them are part of this quorum controller. So each of these nodes will maintain a replica of this metadata partition. Now let's see how a metadata information that we are going to store inside this metadata topic will look like. For example, if we are creating a Kafka application topic, then the metadata for this Kafka application topic creation will look like this. That is, it will contain the topic ID, that is the ID of the topic that we are creating. And if we are creating this topic with only one partition, then the metadata will also contain information about the partition ID. So we are creating only one partition for this topic, so the partition ID will be 0. And if we are creating three replicas for this partition, since we have like three different nodes acting as brokers, and let's imagine that the ID of this broker is 0, ID of this broker is 1, and ID of this broker is 2. And if all these three brokers are in sync and up to date, then the ISR information will be 0, 1 and 2, since the replicas on all these three brokers are in sync and up to date. And the leader is 2. This means this broker containing the replica of this partition is the leader for this partition. So the leader is 2. So this is how a metadata will look like for a Kafka topic. I mean when we are creating a Kafka topic. And then this metadata will be stored inside this metadata topic. In order to prevent this metadata topic from keep growing indefinitely, a portion of this metadata topic will be truncated periodically and this truncated portion will be removed from this metadata topic and it will be stored inside the disk of the node. This truncated portion that is stored inside the disk is referred to as snapshots. This is because the metadata creation will continue to happen as long as we are operating the Kafka cluster. Therefore, we need to stop growing this metadata topic indefinitely. Otherwise, after a certain point of time, it will become a bottleneck to manage this metadata topic. So that's the reason we are truncating a portion of this metadata topic periodically and storing them as snapshots. Therefore, the data retention policy for this new metadata topic is called as snapshot. This is a new data retention policy that is being introduced just to support this metadata topic. For example, whenever you are creating a Kafka application topic, you might choose the data retention policy as delete. This means any data that is stored inside the Kafka application topic that is older than 7 days will be deleted from this topic. Similar to that, in order to support this metadata topic and the concept of snapshots, a new data retention policy called as snapshot has been introduced. I will explain more about snapshot later in this video. Now, among all these controller nodes that are part of this quorum, one of the controller nodes will be acting as the leader. This node that is acting as the leader is called as active controller, whereas all the remaining controllers that are part of this quorum are called as followers or standby controllers. Only the node that is acting as the active controller will be performing all the write operations into the metadata topic or the metadata partition. That is, the replica that is being managed by the active controller is called the leader replica for this metadata partition. All the remaining replicas that is being managed by the standby controllers are called as follower replicas for this metadata partition. This is similar to a partition replica concept that we discussed earlier for any Kafka application topic. Once the active controller finishes writing the metadata inside this leader replica of the metadata partition, then all the standby controllers will make a fetch request or read request to the active controller, and then they will read only the latest metadata from the leader replica, and then they will update their corresponding follower replicas. This is similar to how a consumer application will read only the latest offsets from a Kafka application topic. For example, in this case, the active controller has finished writing metadata up to offset number 3, whereas the follower controllers or the standby controllers have read the metadata only up to offset number 2. So in this case, both of the standby controllers will make a fetch request to the active controller only for the latest offset, that is offset number 3, and then they will update their corresponding follower replicas. In case the active controller fails, then one of the standby controllers will become the new active controller. In the older architecture of Kafka, that is the Kafka which runs with Zookeeper, if the controller fails, then the new controller will be elected by the Zookeeper. But in the new architecture of Kafka, if the active controller fails, then one of the standby controllers will become the new leader. But how this leader election will be done? This is something that we will discuss later in this video. Also, in the old architecture, that is the Kafka which runs with Zookeeper, the metadata replication is done by means of RPC calls. That is, the metadata will be stored only inside the Zookeeper, and then the controller will load the metadata from the Zookeeper or replicate the metadata from the Zookeeper by means of RPC calls. Whereas in this new architecture, we will not be having only one controller, but we will be having a quorum of controllers, and all these controllers will take part in this metadata replication by means of event source storage model, which is what we discussed so far. That is, among this quorum of controllers, one of the controllers will be acting as a leader, and it will be storing all the metadata into a separate Kafka topic as a sequence of events, and these events will be versioned by means of offsets. Then this metadata will be communicated or replicated to other controllers that are part of the quorum in such a way that other controllers will read only the latest metadata from this metadata topic. Since all these controllers replicate the metadata in real time by reading only the latest offset of the metadata topic, we will not be having the problem of divergent views which we discussed earlier between Zookeeper and controller. In addition to storing the metadata inside the metadata partition, each controller will also keep a copy of the latest metadata inside their main memory, that is referred to as metadata cache. That is, whenever a controller commits an offset to the metadata topic, it also keeps a copy of this offset inside their metadata cache. This is mainly done for performance reasons. Now let's imagine that one of the standby controller fails. Then in this case, when this controller is restarted, it will first make a fetch request to the active controller and read all the latest offsets of the metadata that it has missed since its failure. Then it can start operating again. In case the active controller itself fails, then one of the follower controllers will become the new active controller. And when it becomes the new active controller, it already has all the latest metadata in its metadata topic. In addition to that, it also has a copy of its latest metadata in its metadata cache. So it can immediately start taking the new role and immediately start operating the Kafka cluster. That is, the controller failover in this new architecture is near instantaneous. Whereas in the older architecture, whenever the controller fails, the Zookeeper will elect a new controller, and then the new controller has to load the entire metadata from the Zookeeper, and only then it can start operating the Kafka cluster. So until this entire loading process is done, the entire Kafka cluster will be unavailable. Whereas in this new architecture, the new controller already has all the latest metadata in its metadata topic. In addition to that, it also has a copy of the latest metadata in its main memory, that is in its metadata cache, so it can start operating the Kafka cluster immediately. This is one of the biggest advantages of having the metadata cache. Similar to how all these controller nodes maintain a replica of the metadata partition and then replicate the metadata, all the broker nodes also maintain a replica of the metadata partition and then they replicate the metadata. In addition to that, all the broker nodes also maintain the latest committed metadata inside their metadata cache. The broker nodes in this context are called as observers. That is, even though the broker nodes replicate the metadata, they can never become an active controller if the current active controller fails. This is because the broker nodes are configured to act only as brokers, and hence they are never part of the quorum of controllers. Only the controller nodes that are part of the quorum of controllers can become an active controller if the current active controller fails. Hence, the broker nodes only replicate the metadata topic, but they don't manage the metadata topic. When I say manage the metadata topic, this means writing into this metadata topic. As I explained before, only the active controller can write into the metadata topic, and if the active controller fails, one of the standby controllers will become the new active controller, and then this new active controller will continue writing into the metadata topic. So the broker nodes can never write into the metadata topic. The broker nodes also replicate the metadata because they also need metadata information like ISR, leader information, which I explained before. In the old architecture, this metadata information to the brokers will be updated periodically by the controller by means of RPC calls, whereas in this new architecture, all the brokers replicate the metadata from the active controller by reading only the latest offset of the metadata topic. Hence, for this reason, we will not have any problems of divergent views which we saw earlier between the controllers and the brokers. There is also one more advantage of having this entire metadata replication inside all the brokers. In case if you want to configure this broker also as a controller later, since this broker already has all the latest metadata in its metadata replica, it doesn't have to load the entire metadata from the active controller. So when you configure it to act as a controller, it can quickly act as the controller. In case if this broker fails, similar to what we discussed earlier in case of a standby controller failure, this broker, when it becomes active again, it makes a fetch request to the active controller and loads all the metadata that it missed since its failure. This is how a failed broker catches up with the missed metadata loading process. So to summarize, every node that is part of the cluster, that is whether the node is a controller node or a broker node or a combined node, every node will maintain a copy of the metadata topic and then it will replicate the metadata. The protocol to implement the Quorum controller, that is how all the controller nodes that are part of the Quorum replicate the metadata, and then how an active controller is selected. The protocol to implement these two concepts is called as Kafka Raft protocol or simply Kraft protocol. I will explain about this Kafka Raft protocol shortly in this video. With this, we have now seen how Kafka works in the background without Zookeeper and still manages the metadata by itself. Now, I will explain the concept of snapshots on a high level. As I mentioned before, the metadata topic where we are going to store the metadata of the Kafka cluster in the new architecture by default will have the new data retention policy called as snapshot. This means periodically a part of the metadata topic will be stored as snapshots inside the disk in a file. The snapshotted portion will then be truncated from the metadata topic. We are doing this in order to prevent the metadata topic from growing indefinitely. This is because the metadata creation will continue to happen as long as we are going to operate the Kafka cluster. Therefore, we need to stop this metadata topic from growing indefinitely. Otherwise, it will become a performance bottleneck to manage this metadata topic in the long run. So how this concept of snapshot works? Now I have a controller which is writing the metadata into its metadata topic. So whenever the controller finishes committing the data inside its metadata topic, it also loads the committed data into its memory, that is the metadata cache. Then periodically all the data that is committed into the metadata topic as well as loaded into the memory will be taken as a snapshot, and this snapshot will be stored inside the disk in a file. Then the snapshotted portion will be truncated from this metadata topic. So in reality, whatever the data that is contained inside this metadata topic plus the snapshot will give the complete metadata of the Kafka cluster. By this, we also realize that the metadata topic contains only the latest metadata, and all the data that is in the snapshot will definitely be older than the data contained in the metadata topic. Now, let's see how the concept of snapshot works in the case of a node failure and restart. Now, I have this active controller which has finished committing all the data until offset number 12 into its metadata topic, that is the leader replica of the metadata partition. Since it has committed the offset number 12, it also loads them into its main memory, that is the metadata cache. Also, it finishes snapshotting all the data until offset number 9 into its snapshots. Now, I have another node which has finished snapshotting all the data until offset number 3, and also it has finished committing all the data until offset number 6. But after this node got failed and now it is restarted. That's why you don't see any data into its metadata cache. As I explained a couple of minutes before, all the data contained inside the snapshots will be older than the data contained inside the metadata topic. So this node, after the restart, will first load its recent snapshot into its metadata cache. And after this, the node will load all the data contained inside the metadata replica into its metadata cache. And after this node will make a fetch request to the active controller for all the new metadata contained inside the leader partition. Now the active controller will find out that the start offset of the leader partition is greater than the offset required by this node, because this node now requires the metadata starting from the offset number 7. So now the active controller will check which snapshot contains the relevant data required for this node. It finds out that S3 contains the data starting from the offset number 7. Hence, the active controller will return the snapshot ID S3. Now, this node will load all the data contained inside S3 into its metadata topic. Once it finishes committing this data into its metadata topic, it then loads this data into its main memory, that is the metadata cache. And after this, the node once again makes a fetch request to the active controller and starts loading all the new metadata contained inside the leader partition into its own replica. So this is how the concept of snapshots is handled in the case of a node failure and restart, and it is used to restore all the metadata that the node has missed since its failure. Now let's see what is actually a Kraft protocol. As I explained before while I was discussing the architecture of the Kraft protocol is actually a protocol to implement two different mechanisms inside the Quorum controller. The first mechanism is a mechanism for replicating the metadata across all the controller nodes inside the Quorum controller, and then a mechanism for electing the active controller, because in case of a Quorum controller, we don't have an external system like Zookeeper to elect a new active controller when the current active controller fails. That's why we also need a leader election protocol. So the first one is replication protocol. In case of Kafka, Kafka uses the concept of primary backup mechanism for replication. So what is actually a primary backup mechanism? If a partition has multiple replicas, then the leader replica will take all the write operations, for example, the writes coming from the producer applications. Then the leader will push the data to all of its followers. That's why primary backup mechanism is based on the concept of push, that is, the leader will push the data to all of its followers. In case of Kafka, Kafka also uses the concept of primary backup mechanism for replication, but it uses pull-based method. That is, if a partition has multiple replicas, then the leader replica will take all the write operations, for example, writes coming from the producer applications. And then all the follower replicas will make a fetch request or read request to the leader, and then they will update their corresponding replicas. So in case of Kafka, the leader won't push the data to the followers. Instead, the followers will pull the data from the leader. Then the leader will consider the write operation as committed only when it receives an acknowledgement from all the followers. In the case of quorum controllers, we cannot apply the same concept of primary backup based on pull-based mechanism for replicating the metadata across all the controller nodes. This is because in this case, the active controller, which is also the leader controller, has to wait for an acknowledgement from all the follower controllers about the replication status. This will lead to an increase in the waiting time or the replication latency for the active controller. Now, if we are scaling this quorum controller by adding more and more controller nodes, this will further lead to an increase in the waiting time. An increase in the waiting time means decrease in the performance of the Kafka cluster. This is because all these controller nodes are dealing with the metadata of the Kafka cluster. So that's why in case of a quorum controller, we are going for another replication mechanism called quorum-based replication. So first, what is actually a quorum? Quorum is based on the concept of majority instead of all. So in quorum-based replication, if a partition has multiple replicas, then the leader replica will take all the write operations. For example, the writes coming from the producer applications. And then, similar to a pull-based method, the followers will make a fetch request to the leader and then they will update their replicas. But the real difference between the quorum replication and the primary backup mechanism is, in case of a quorum replication, the leader will commit the write operation when it receives an acknowledgement from a majority of followers, including itself, rather than waiting for all the followers. So in this case, what is an acknowledgement? Imagine that a follower sends one fetch request to the leader. Now, when the follower sends a second fetch request to the leader will assume that the first fetch request write operation has been completed by the follower, and hence it takes the second fetch request coming from the follower as an acknowledgement for the first fetch request. So in quorum-based replication, we are doing a trade-off between the replication latency and the delivery guarantee. That is, the active controller is not waiting for an acknowledgement from all the follower controllers. In this way, we are reducing the replication latency or the waiting time for the active controller. But at the same time, the active controller is not ensuring that the metadata has been replicated across all the follower controllers. So we are not guaranteeing whether the metadata is delivered across the follower controllers or not. But this is a worthy trade-off. That's the reason we don't have the concept of in-sync replicas for the controller replicas, since the active controller is not really ensuring the delivery of the metadata across all the follower controllers. This concept of quorum-based replication is introduced by a protocol called as Raft protocol. So in case of a Raft protocol, if we want to tolerate n failures, then the quorum need to have 2n plus 1 replicas. So for example, if the value of n is 3, then the quorum controller need to have 7 controller replicas. So in case of 7 controller replicas, the majority is 4. So even if 3 controller replicas fails, and if the active controller does not receive an acknowledgement from 3 controller replicas, it can still live because it still has an acknowledgement from 4 controller replicas including itself, and this is enough for the quorum controller to operate. So the next mechanism is the leader election protocol. So why we need a new leader election protocol for a quorum controller? So now let's imagine that we have a Kafka cluster with one Kafka topic, and this Kafka topic is having one partition with 3 replicas. Now this replica is the leader replica. In case if the broker containing this leader replica fails, then among the remaining 2 follower replicas, one of the replicas has to be elected as the new leader, and this is done by the controller. However, the same concept of the leader election cannot be applied for a quorum controller. Now let's imagine that we have a quorum controller with 3 controller nodes, and this is the active controller. So the replica of the metadata partition managed by this active controller is also the leader replica. Now if the active controller fails, then we are also losing the leader replica. So among the remaining 2 follower replicas, one of them has to be elected as the new leader replica. However, we also lost the active controller. So we don't have any external system to elect the new leader replica. And that's the reason why we need a new leader election protocol for the quorum controller. So in this new leader election protocol, all the controllers that are part of the quorum controller are considered as a voter. Now, when the active controller fails, then one of the voters, that is one of the follower controllers, will attempt to take the role of a candidate for becoming the new active controller. Now, this candidate will request votes from all the remaining voters. If this candidate receives a majority of votes, including one from itself, then this candidate will become the new active controller. Suppose if this candidate does not receive a majority of votes within a specific time period, then the election process for this candidate will be considered as a failure. And then another voter will attempt to take the role of the candidate, and then the entire process will repeat. The concept that is used for the voting process inside the leader election is actually based on the voting process used for the Kafka partition leader election, which is based on the concept of epoch. However, I am not explaining this concept of epoch in detail here. I have provided a link for an excellent blog in the description that explains this concept of epoch used for the voting process inside this leader election in detail. Now let's see why we call this new protocol used by the quorum controller as Kraft protocol. For replicating the metadata across all the controller nodes inside the quorum controller, we use a method called quorum replication, which is implemented by the Raft protocol. But at the same time, for actually replicating the metadata, we still stick to the pull-based method used in Kafka. That is, all the followers will make a fetch request for replicating the metadata. And then, for electing the active controller, we introduce a new leader election process, what we discussed in the previous slide. But at the same time, this leader election process uses the epoch concept for the actual voting method. Thus, we could clearly see that this new protocol is based on a mix of Raft as well as Kafka protocols, and hence we call this new protocol as Kraft protocol. By now, I believe I have explained most of the things that we need to be aware of the new Kraft architecture. Now let's try to compare the performance of the Kraft architecture against the architecture of the Kafka based on Zookeeper for certain critical operations that we discussed before. For example, the controller failover. In case of a controller failover, whenever an existing controller fails, first the Zookeeper will elect a new controller, and then this new controller has to load the complete metadata of the Kafka cluster from the Zookeeper. Since the controller is also a broker, it is possible that the failed controller might have hosted Kafka application topics and partitions, and it is also possible that some of those partitions might also be the leader partitions on the failed controller. So when this new controller is elected and when it finishes loading the metadata from the Zookeeper for all those failed leader partitions, the new controller has to elect the new leaders, and then it also need to update the ISR information. Once this is done, the new controller has to persist the updated metadata inside the Zookeeper. And once this persistence is done, then the new controller has to propagate the updated metadata to all the remaining brokers inside the Kafka cluster. The time required to perform the overall operation is equivalent to the order of the number of partitions. That is, as the number of partitions increases, then the metadata about these partitions will also increase, and hence the overall time required to perform this entire operation will also increase. However, the most painful operations are the place where the new controller has to load the complete metadata from the Zookeeper. Until this is done, the entire Kafka cluster will be unavailable for the Kafka clients. And then the next painful operation is the area where the new controller has to persist the new metadata inside the Zookeeper. This is because as the amount of metadata increases, then the number of IO requests between the new controller and the Zookeeper will also increase. Now, if we look into the new Kraft architecture, when the current active controller fails, then one of the follower controllers will become the new active controller. And since this follower controller also has all the latest metadata in its own replica of the metadata topic, and since it also caches the latest metadata in its metadata cache, it can quickly take up the role of the new active controller and can quickly start operating the Kafka cluster. And in case if this failed active controller is a controller only node, that is, if this node has been configured to act only as a controller and not as a broker, then this new active controller doesn't have to perform any activities like electing new leaders or updating the ISR information, because there won't be any Kafka application topics or partitions in the failed active controller. However, if the failed active controller is a combined node, that is, if this node has been configured to act both as a broker as well as a controller, then there will be definitely Kafka application topics and partitions inside the failed active controller, and some of those partitions might also be leader partitions. Hence, in this case, the new active controller has to elect the new leaders for all those failed leader partitions and also need to update the ISR information. However, for this new controller, these activities are just an entry into the metadata topic. The new active controller doesn't have to persist the information, that is the updated information, into any external system like Zookeeper. As we discussed before, brokers also replicate the metadata into their own replica of the metadata partition. So this means whenever the new active controller updates the new leaders or the ISR information, since brokers also replicate the metadata, they will also have quick access to this updated metadata information. Whereas in the old architecture, whenever the controller performs an update in the new leader or the ISR information, the controller has to propagate the updated metadata information to the brokers by means of RPC calls. Hence, there are more chances for having a divergent view of the metadata between the controller and the brokers, whereas in the new architecture, it is not the case. Similar to the controller failover, we can also argue the performance difference between the Kraft-based architecture and the Zookeeper-based architecture for other critical operations like controlled shutdown or uncontrolled shutdown and recovery. Now let's check the performance evaluation conducted by Confluent for Kraft architecture over Zookeeper-based architecture. So you can clearly see that the performance of the Kraft architecture is significantly higher compared to the performance of the Zookeeper-based architecture. For example, in case of an uncontrolled shutdown and recovery for a cluster with 2 million partitions, the Zookeeper-based architecture takes around 8 to 9 minutes, whereas the Kraft architecture takes less than a minute. Now, before wrapping up our session, let's try to discuss some of the major advantages of the Kraft architecture. With Kraft, Kafka is not a heavyweight infrastructure anymore. This is because we don't have an additional system like Zookeeper, and hence, if we want to have Kafka in our infrastructure, we need to deploy only the Kafka cluster and not the Zookeeper cluster anymore. So moving forward, Kafka will be a single process deployment. Since we don't have the Zookeeper system anymore, we don't have to worry about configuring or maintaining an additional system. This makes the life of the Kafka administrators simple. As I discussed before, in the new Kraft architecture, there won't be any divergent views between the controllers and the brokers, because in the new Kraft architecture, the brokers also replicate the metadata. Also, there won't be any divergent views among all the controller nodes inside the Quorum controller. For all those time critical operations like controlled shutdown, uncontrolled shutdown and recovery, and controller failover, in the new Kraft architecture, the time required to perform these operations is not equivalent to order of the amount of partitions. Hence, in the Kraft architecture, we can now have more number of partitions compared to the Zookeeper-based architecture, because adding additional partitions will not impact the time for these operations. As a consequence of this, Kafka can now support millions of partitions. One more important advantage of the Kraft architecture is whenever we are creating a new Kafka application topic or whenever we are deleting an existing Kafka application topic, the time required to perform such operations is equal to order of 1 because such operations just requires an entry into the metadata topic. Whereas in case of a Zookeeper-based Kafka architecture, the time required to perform such operations is equal to order of n. This is because whenever we are creating a new Kafka application topic or deleting an existing topic, the controller will load the full list of topic names from the Zookeeper. Because whenever such incident happens, the Zookeeper will notify the controller that a topic change has happened but doesn't notify which topic exactly has changed. So these are some of the major advantages of the Kraft architecture compared to the Zookeeper-based architecture that are worth mentioning. I have provided a link in the description that also explains lots of other advantages of Kraft over the Zookeeper-based architecture. Now some information on the release and migration of Kraft. So Kraft was made available initially as part of the Kafka version 2.8. As part of this version, an early access was made available mainly for testing purposes. Then as part of the version 3.3.1, Kraft was marked as production ready. That is, moving forward, we can already deploy Kafka clusters in Kraft mode inside our production environment. Then as part of the version 3.4, which is also the latest release when I was making this video, an early access for migrating the Kafka clusters based on Zookeeper to the Kafka clusters based on the Kraft protocol is made available. We call this release as bridge release. In the upcoming version, that is the version 3.5, this bridge release is expected to be marked as production ready. Some important things that you need to note. So moving forward, please do not use the Zookeeper flag. Instead, use the Bootstrap server flag for any of your Kafka clients like producers, consumers, or other Kafka clients like Kafka configs or Kafka topics, whatever it is. I can already test the support for the two-way SSL security in the Kraft mode. However, I do not find any enough documentations on the SASL yet, both on the Kafka website as well as on the Confluent website. However, I will keep you updated on this thing in the upcoming days. Now let's try to summarize what we discussed so far in this video. First, I started with the explanation of the current Kafka architecture, that is the Kafka cluster which runs with Zookeeper. And then I listed out all the current limitations that we are facing today because of the presence of Zookeeper. The most important limitations concerned with complexity and scalability of the Kafka cluster. In this context, I also explained about some important critical operations like controlled shutdown, uncontrolled shutdown and recovery, and controller failover. And then I explained the logic behind removing the Zookeeper completely from the Kafka ecosystem. Followed by this, I explained in detail about the architecture of the Kafka cluster which runs without Zookeeper, that is the Kafka cluster which runs in Kraft mode. Then, on a very high level, I explained the Kraft protocol, that is the protocol behind replicating the metadata as well as the protocol behind the leader election for active controller. And then I listed out some of the major advantages of running the Kafka cluster in Kraft mode over the Kafka cluster based on Zookeeper. And finally, I also gave some information about the release and migration of the Kraft. With this, we have come to the end of today's discussion. In the next video, I will explain how to launch a Kafka cluster in Kraft mode. In case if you have any questions or doubts, please feel free to list them out in the comment section. So see you in the next video. Until then, I wish you good luck in your Kafka journey.